Hello everyone, this is Amy. Today we're going to talk about quantum spin. You may have heard of some experiments about quantum spin that shows the uncertainty of it, and you may be interested in how that makes sense. If so, then this is the right place for you to improve your understanding. Firstly, we shall talk about Pauli matrices, which are operators that represent the spin one over two particle along the x, y, and z axis. You should consider them as constants. It is important to know that in quantum mechanics, observables are represented by matrices, and the outcome of the measurement is an eigenvalent of a matrix. The basis state vectors are eigenvectors of the matrix, so they're correlated. As for how to find the eigenvalence of a matrix, you should use this equation, but this isn't important for this topic, so I'll not talk about it here. Then we'll learn about matrix multiplication. For simplicity, let's take 2 by 2 matrices as an example. We are multiplying these matrices. We should take each full of matrix A, then rotate it and multiply it by each column of B using inner product. Each multiplication like this will get a scalar. Then simply put the scalars in the correct position, the vertical position from A and the horizontal position from B. With this, you'll find that generally matrix multiplication doesn't commute, so if they commute, what can happen? If the two matrices commute, there exists a set of states that are simultaneously eigenstates for both matrices. This will imply that the observables they represent can be simultaneously known with certainty. It's alright if it's difficult to understand at the moment. Here, we should first prove this now. Using the definition of eigenvalence we have for eigenvalence lambda and eigenvectors v of A, AB equals to lambda v. Consider matrix B, provided AB equals to BA. That means they commute. Therefore, when we multiply B by each side of the equation, we get ABV equals to lambda VB, which means BV is also an eigenvector of A. We can say that B preserves the eigenspace of A. Imagine the basis state vectors overlap. A state vector there can represent a state that is simultaneously basis state for both quantities. In other words, there exists a set of quantum states in which both observables have definite valence. For a clearer explanation, I'll visualize this. We shall draw a plane for state vectors, as what we did in the first episode. In linear algebra, one eigenvalence corresponds to one eigenvector. That means for one possible basis state, we have one state vector, and all the state vectors on the plane can be represented by a linear combination of the bases, including superpositions. Let's consider this set of bases. We rotate the bases to get another set of bases and say they're connected quantities. Here, psi is certain valence for this quantity, which means it is not a superposition. But if we focus on the other set of bases, you'll find that psi is a superposition. When psi becomes certain along one axis, then the spins on the other two axes become uncertain. Okay, time to use some visualization scripts. Here I'm showing my scripts to visualize the certainty of quantum spin. First, the code includes 3 Pauli matrices that we have learned earlier. Then I use NumPy to get their eigenvectors. As you can see here, I've got a slider for the angle between the state vector and the x-axis. Since state vector's length should always be 1 because of the probabilities conservation law, it should be possible to calculate its column vector based on the angle. Then the code below can project the state vector onto the eigenvectors of the Pauli matrices. It means the dot product between the state vector and one of the eigenvectors. Here, dot product is equivalent to the cosine the angle between them. This is the fundamental operation in quantum mechanics. If we run the scripts, we can see vectors in different colors. The red one is the state vector and can be controlled by the slider. The others are the basis vectors for Pauli matrices. The text on the right-hand side shows spin along different axis probabilities. You can see the values p positive y and p negative y won't change. That's because these eigenvectors are complex, which will need higher dimension if we draw these eigenvectors. As we drag the slider to let the particle spin along negative x-axis, the other components show uncertainty. Moving it to let it be certain along negative z-axis, then the other components show uncertainty again. Therefore, the uncertainty of quantum mechanics can be well explained here. The scripts are also under the video. You can try if you want. Thanks for watching.